So I'll start with a question. Let's say I have given you an array of size n. Okay, so there is an array of size n and there is an integer k. Okay, so what you're supposed to do is you're supposed to find the maximum element from every window. Window is just like a subarray. So you have to find maximum element from every window or subarray of size k. This k is this one. How many subarrays of size k will be there in an array of size n? Okay, so one of you is saying n minus k. Does someone feel it will be greater than n minus k? Can you take an example? If let's say n is equal to 5 and k is equal to 3. If n is equal to 5 and k is equal to 3, there will be n minus k plus 1. Yeah, very good. So n minus k plus 1 different subarrays will be there. So let us take an example to make things much more clear. Let's say the elements are 10, 1, 9, 7, 3. There are 3 elements and let's say the window is of size 3. So this is the first window of size 3, this is the second window of size 3 and this is the third window of size 3. Are there any other windows? Do you see any window of size 3 that I have missed over here? No, I haven't missed. Okay, so the number of windows is n minus k plus 1. These many windows are there. Why? It is so because every window has a starting index. The starting index of this window is 0. The starting index of this window is 1 and the starting index of this window is 2. Can I say in generic terms that the starting index of last window will be n minus k? The starting index of the last window will be n minus k. For the first window, the starting index was 0. For the second, it was 1. And for the last, it is k. So how many terms are there from 0 to n minus k? Number of terms from 0 to n minus k is n minus k plus 1. Right? And that is the reason these many windows are there. Right? So these are the total number of windows. Now you understand what you're supposed to do, right? For that, I'll take a longer example. So let's say 5, 3, 6, 4, 9, 8, 7, 11, 2 and 15. K is equal to 4. K is equal to 4. So for every 4 sized window, so guys, the windows of size 4, first window is this. And what is the maximum from here to here? It is 6. Second window is this. And the maximum from 3 to 9 is 9. Next window is this. And the maximum in 6, 4, 9, 8 is 9. Next window is this. 4, 9, 8, 7. Maximum is 9. Next window is from here to here. And the maximum is 11. Next window is from 8 to 2. Still maximum is 11. And next window is from 7 to 15. The maximum is 15. Okay. What is the brute force way to do this? The brute force way is to consider every window, and after considering every window, just iterate from the starting index to the last index of that window and find out the maximum and print it. Now, given the values of n and k, can you accurately type the time complexity of this approach? Yes, it will be n minus k plus 1 into k, because number of windows which I will consider will be this, which is n minus k plus 1, and for every window the number of iterations will be equal to the number of elements in that window, and number of elements in every window is k. So it will be this. Now, do you feel that this is approximately order n square? Because if you replace k by n by 2, both the terms will be n by 2 each. So if you replace k by n by 2, this thing will be n by 2 plus 1 and this thing will be n by 2. So it will go till order n square. Right? So this is something like order n square algorithm. Can I improve it? Because think of it in this way, if the question was to find the sum of every window, would you have done it in order n time? Yes or no? Yeah, you could have done it. Because there what you were doing, you were considering every window of size k, Now whenever you were moving a window, then only few things were changing. The first element of last window was getting kicked out and the new element was getting in. So your current sum was current sum minus this thing and plus something. So this way you used to do it. How many of you are getting a feel of sliding window here also? Tell me one thing, why sliding window is not going to work over here? Let's say you calculated the maximum for first window. Everyone just have your laser sharp focus at the board. You calculated your maximum of the first window. That will take you order k time. Yes or no? That will take you order k time. Now when you are shifting this window, let's say you shifted this here. If let's say the element to go from here was smaller than the max. If the element to go from here was smaller than the max, will the answer for the next thing change? Just use your brain and tell me, will the answer for next window change? No is not the right answer because it can change. What if the incoming element is greater than the max? Yeah, it depends upon that. Did you get that? But whenever the outgoing element exhibits this nature, I can say that my answer for the next window will be max of previous max, which was 6, comma, incoming element. Whichever is max of these two, that would be the answer for my next window. Can I say it? Yes or no? I mean, this is common sense. This is very easy to say, right? But if that is not the case, if let's say this was a 6 here also, and this was a 6 here and this was a 5 here, and then this was a 1 here. In that case, could you tell it? You could not tell it, right? Because if this 6 is going, what if there are some more occurrences of 6 over here? And also, if there are no more occurrences of 6 over here, what is the second minimum after 6? So tracking the second minimum or tracking if this thing is already there or not, there are so many things that come up. And just tracking first minimum and second minimum is not going to help, because when you move it, that second minimum might also get kicked out. So in that case, you would need to know the third minimum now. So that way it is not going to work. It is not as easy as the sum thing. Okay, so now we are going to learn that how we can use better data structure to get my job done. So what is it about stacks? So if you think of stack is like insert at front. I am going to refer top as front. Insert at front and delete also at front. But queue is like insert at rear but delete at front, right? Now there is a very, very important data structure. So let's think of a data structure, okay, which has, let's say, 1, 2, 3, 4, and it supports 4 operations. Those 4 operations are insert front, insert rear, and then delete front as well as delete rear. So it supports all these operations. So what is the meaning of insert front? Insert front means that I can insert anything at, let's say, this end, and insert rear means that I can insert anything at this end. So I was able to insert at this end using queue also, but I was not able to insert something at this end using queue. Similarly, delete front means I can delete something from here, and delete rear means I can delete something from here. So both the ends are open for insertion as well as deletion. I repeat it, both the ends are open for insertion as well as deletion. 2 ends, 2 distinct operations, so 4 total operations. Now the data structure that supports this functionality is called as deque. De means doubly ended, and this is clearly doubly ended because both the ends are open to support both the operations. Okay, so I have just given you an introduction to doubly ended queue. Okay, I have not told you how to apply that in this case. I'll come to that later. Can someone imagine how would this data structure be getting implemented? I mean, you implemented stack by using something as easy as arrays. You implemented queue using arrays. So can someone imagine how would this data structure be getting implemented? So first I'll talk about a very naive implementation, and before that I'll move on to linked list. Just think of it in this way, that there is a, guys, this is just for, you know, hypothetical purpose to make you at least realize that yes, this can be implemented. Let's say there is a huge array, infinitely long array, going in this direction also and going in this direction also. So you can have some middle section of it where there are elements 1, 2, 3, 4, and now you track this end as well as this end. And so now you can insert at this end, delete at this end, insert at this end, delete at this end. So this is one way, that take a very huge array and in the center of it start with the elements. So this is the easiest thing that I can do, but this has got its cons. What are the cons? That what if there are so many insertions over here? After that, if there is again an insertion over here, I cannot insert it, although these spaces are vacant. So to avoid this thing, we use dynamic data structures, and those are like linked list. So linked list can be really handy to implement it, because a linked list looks somewhat like this, and now you can track head and tail. And if somebody let's say tries to insert something here, you can bring that thing here, connect it to this, and bring tail here. And if somebody wants to insert something here, insert it, bring a new node, connect it, and make this new node as the head. Same thing is for deletion also. To delete, one more thing. So to delete this thing, you just have to let go of this thing and make head as head next. And to delete this thing, because you cannot move from here to here, one easy way is to track the parent of this. So you can simply track the previous parent also. So in that case, you can let go of this and let the T come over here. Another way is to use doubly linked list, but if you are tracking the last node and second last node, then that might not be as essential. The best way, however, is to use that doubly linked list. The reason I have not spoken about that is because we have not learned it. So go off it for now. So all these operations are done in order one time. Okay, can I say that such a kind of data structure can be used to implement stack operations also and queue operations also? Can I say that? Yeah. So deque is empowered with the functionality of stacks as well as queues. Now let's move on. Now let's talk about this problem. Let's say I have an array of size n, and my k is equals to 7. So let's say here I have to consider all the windows of size 7. So let's say the first few elements were 10, then 3, then 2, and then 1. So I have to consider first 7 elements. So let's say after this came an element called 9. And then there are many more elements to come. So let's say this 9 came over here. Now I have a question to ask from you. So let's say the first window of size 7 was this much. Let's say it was. And there were 2 more elements here. This was the first window of size 7. Guys, can I say one thing? That let's talk about the elements that are coming before 9. So all the windows that are starting before 9, let's say windows starting from 3, or windows starting from 2, or windows starting from 1. This window which starts from 3, this window which starts from 2, this window which starts from 1. Can I say that all of them will definitely contain 9? Yes, they will definitely contain 9, because all those windows are going to be the same size as this window. So if this is of the same size as this and you're sliding it, the 9 will definitely be there. Okay. Similarly, when you are sliding this, again 9 will definitely be there. Again you are sliding this 9 will definitely be there. So any window that comes at 9 or before 9 in the range of k is definitely going to contain this 9 within it. Now my question from you is simple. If this 9 is there, will it allow 3 to be the answer in this window? It won't, right? Similarly, can I say that this 9 will not allow this 2 to be answered in this window, right? Similarly, can I say this 9 will not allow this 1 to be the answer in this window, right? So can I say that when you are considering a window of size k, As long as you are getting decreasing set of elements, everything is good. But the moment you get an element which is larger than few elements, then this thing is going to render this, this and this as useless. So because of this 9, which is greater than all those elements are being considered useless. Okay. Now let's say after this 7 comes. So see, they are useless, gone. Okay, they are never going to be answer of any window. They are never going to be answer of any window at all, because the answer of the window that starts from 3 will either be 9 or will be something which is greater than 9, which will come after 9, right? Similarly for 2 also, and similarly for 1 also. Cool. Now let's say this 7 comes. Okay, can this 7 render this 9 useless? No, because the window that starts from 9 can be the answer of that. But had this 7 instead been 17, in that case I could have said that, hey, this 17 is going to make the life of this 9 useless. Okay, one of you typed depends. That is incorrect, right? Because see, this window is of size k. Now any window of size k that starts from 9 will definitely have 17 in it. And because it has 17 in it, this 17 will not allow this 9 to be the answer. Either the answer will be 17 or something which will be greater than 17. Can I say that the useful elements of a window are the elements in descending order? I can say that, right? So just imagine a case like this. Let me give you an example again. Let's talk about this window. So you had 10, you had 3, you had 2, you had 1, you had 9, 17. How many of them are there? 6. Let's say one more. 10 again, or 11 again. And then there are certain other elements. So this is your first window of size k equals to 7. So let's say when you are going through this window, first you meet this 10, so you keep this 10 somewhere. Now you meet this 3. So this 3 is smaller than this 10. So can I say that, hey, this 3 might not allow this 10 to be the answer? Is it correct to say? It is not correct to say, right? But had it been 13, then certainly this 10 was useless, because any window of size k that starts from 10 will contain this 13, and this 13 would have rendered this 10 useless. So if you are seeing an element which is smaller than the the element standing at the front, in that case you should consider it. Similarly, when you come to 2, you will compare this 2 with 3. What will you do? Can 2 discard this 3? 2 can't discard this 3, right? Because 2 is smaller than 3. So this 2 will be considered as it is. Similarly, 1. Can this 1 discard any of them? No. Because any window that starts from 2 will have 2, and that 2 is greater than 1. Now comes this 9. The moment this 9 comes, how many elements will be rendered useless? 3 elements will be rendered useless. So for that, what would you want to do? You would want to start popping from here as long as it is possible to pop. So you will continue popping until you meet a strictly larger element. Okay, till that time you will keep just popping. So as a result of that, what will happen when this 9 comes? This 9 will kick this out. When this 9 comes, this 9 will kick that 1 out, kick this 2 out, and kick this 3 out, and then that 9 will come over here. Is it not stack-like operation? Because literally what is happening, that there is this end where deletions are also happening and insertions are also happening. So elements are getting inserted also and elements are getting deleted also. So this is clearly stack-like operation. Okay, had it been 90, this would have kicked this out also. In that case, when you see that your queue or whatever you are using becomes empty, just push it. Okay, cool. Now this 17 comes. So when this 17 comes, you compare it with the top, you find this is greater than the top. So this will never allow any window that starts from 9 to have 9 as the answer, or anyway these were anyways useless because of 9. and now 9 is also useless because of this 17. Okay, so now when the 17 comes, this will kick this out and this will kick this out as well. Okay, and now this 11 comes. Will 11 be a useless element for me? Yes or no? No, it will not be a useless element for me because this 11 is smaller than this. So I'll simply insert this. So now do you realize that the useful elements of the first window, the useful elements of the first window are just 17 and 11. Why? Because any window that starts from here is going to contain 17. Any window that starts from here is going to contain 17. Any window that starts from here or here or here or here is going to contain 17. But the window that starts from here is not going to contain 17. That is what I mean by useful elements. Can I say that whatever this data structure is, the elements will be in decreasing order over here? I can say that, right? So now what is going to happen? Now you have the useful elements of a particular window. Which of these, let's say there were more than 2 useful elements, what would have been the answer for that window? Which element would have been the answer for that window? Can I say 17, which is the element at the starting index, would have been the answer because it is sorted in descending order. This just contains the useful elements and the highest useful element will be at the front and the highest useful element will be the maximum element as well. So can I solve this problem just by using a stack in this way? So I just have a stack. The moment something new comes, I pop and then I push. Can I just use a stack to solve this problem? In other words, I'm asking. I cannot. Why I cannot? Because when the window slides, let's say it slided till here, then till here, then here, then here, then here. When the window comes here, then I would need to let this thing go out. When the window slides, you have to let go of that element. And to let go of that element, you need to kick element from this end also. So I needed insert rear, I needed delete rear, but I need delete front also. Do you see that these 3 operations are required? These 3 operations are definitely required. And because these 3 operations are required, so I cannot solve my problem. See, for these 2, I can use a stack. For these 2, I can use a queue. But for this entire thing, I need a deque. So the right choice of data structure over here is a doubly ended queue. Now guys, tell me one really easy thing over here. How do I decide? So for this window, the useful elements were 17 and 11. But had there been 100 over here, let's say had there been 100 over here, in that case, I would have had 100, 17 and 11, right? Now let's say when I talk about the next window, let's say in the next window, something like 6 comes, okay? So whenever a new element is being welcomed, you will see if you can pop certain elements or not. If you can pop, you will pop them, and in the end you will push it. But it's not just about welcoming a new element, it's also about kicking out the previous element if that is valid to be kicked out. Like here, 100 is at the front, which belongs to the previous window. It doesn't belong to the current window. So should I kick out this 100 or not? I should kick out. Okay. Now let's take the another case. If it was 10, in that case, would you have wanted to kick out this 17? No, right? So do you realize this thing that you have to welcome every time, but you don't have to kick every time. You have to kick only when the element belongs to the previous window and not the current window. And how to make the decision? How to make this decision whether I have to kick or not? Very simple answer it is. So instead of element, can I check if the front is same? That is not the right solution because there can be duplicate elements also. There can be duplicate elements, so that is not the right thing. Instead, store the indices the way you stored indices in next greater element, right? So instead of storing the elements, what you can do is you can store the indices. So the index of this 100 is 0, and index of this 17 is 1, 2, 3, 4, 5, and index of this 11 was 6. Now let's say this 6 comes, whose index is 7. So since this 6 is not greater than any of them, it is not greater than 11 or 17. It is not greater than 11, it is strictly smaller. So you can simply let it be. Okay, you can simply let this index 6 come over here. Sorry, what is this index? This index is 7. Okay, and now how to decide whether this thing can be kicked out or not? How do you decide that? So if you see that this index happens to be smaller than or equals to, let's say this is I. So if this is smaller than equals to I minus k, like this is 7 over here, and 7 minus 7 is 0. So anything that has an index of 0 or smaller will not belong to my current window. So if whatever is at the front, if that index is smaller than equals to I minus k, I have to kick it out. And if that is not the case, if let's say this was 10, then the index of this would have been, 5. So here this 5 is not smaller than equals to 0. So if you just have the index and if you make this check whether the front of your queue is smaller than equals to I minus k or not, you can choose whether to kick it out or not kick it out. So guys, you can simply use your deque data structure to perform the pushes and pops on your behalf, and everything else will automatically get done for you. So deque is defined in this way. This is how it is defined in C++. So your next task, write it. You have to learn how to use deque in your language, which is C++ or Java. So again, very simple. It will hardly take 2 minutes for you to understand. So deque and the data type, here it is integer, and here is the name of that. Now, I'm not sure about the name of operations. You must have things like, push front, pop front, and push back, pop back. And similarly, deque.front gives you this, and deque.rear gives you whatever is at the rear. So now let us take a quick dry run to make things very, very easy for all of us. So let's say you have 10, 1, 2, 9, 7, 6, 5, 11, and 3. Okay, and let's say k is equal to 4. So to prepare your deque, first you will examine your first window of size 4. Okay, so first you will maintain the useful elements of this. To do that, first you will insert the element at index 0 as it is. Now you meet this 1, what will you do? You compare this 1 with 10. Can you tell me what will you do? See, you are just preparing the useful elements for first window. That is what we are doing right now. So this 1 is smaller than 10. So this, had it been 11, it would have made this useless, because everything that starts from 10 would contain this 11. But this is smaller than this, so I need to allow this. What if this was equal to 10? Do you worry about that case? If this was equal to 10, then what would you do? Would you push or not push? The point to understand over here is, see, if this 10 comes over here, if this element is greater than equals to any other element in this window, then this will definitely not allow this to be the answer. The logic for that is because any window that starts from here will definitely contain this 10 also in that. Will definitely contain 10 also in that. And because it will contain that 10 in that window, so I think that 10 can be allowed to pop it out. In other words, I mean to say, let's say instead of 10 over here, there was a 10 over here. So if I had a 10 over here, I can say that, hey, any window that contains this 10, let us forget this was here, let us say this was here. I can say that any window that contains this 10, so this is the window that contains this 10, will also contain this 10. Any window that contains this 10, so this window also contains this 10, and it has this 10 also. Any window that contains this 10 has this 10 also. So if the incoming element is greater than or equal to the previous element, which is your head, it can be allowed to kick that out, because that will be an inclusive member of all the windows which would contain the previous element. But for next subarrays with starting point as the next 10, it should be remembered. What is the issue? What is the exact issue? I don't see an issue over here, because if you move it, see, when you try to push this thing over here, you are actually not pushing this thing, you are actually pushing the index of this. So if the index of this, was coming in that zone, which is I minus k zone. smaller than equals to, greater than equals to this thing, then that would also come, because that is coming much later than that. So the problem would actually never happen. Is everyone getting that? I think it's simple to say it, right? If you are talking about this window, and let's say you were storing the useful elements. So the useful elements for this window was, what is the index here? This is 2, and this index is 3, and then 4, and then 5. This is all in decreasing order, so all of them are useful elements. Now if something new comes, let's say this is 5, this is also smaller than this, its index is 6, so this comes as it is. Now the point is that even if you had a 3, even if instead of 2, 3, you just had a 3, there was no problem at all, because if this 2 can lie in this window, then this 3 will also lie in this window. So the point is that only if you get a next element which happens to be strictly smaller, then it should be, then it cannot kick out the previous element. But even if it is equal to the previous element, it can be allowed to kick out the previous element. And now that's totally up to you. Whether you kick it out or you don't kick it out, things are not going to change a lot. Okay, it's just your implementation choice. Cool. So let's say I have 10, 1, 2, 9, 7, 6, 5, 11, and 3, and your k is equal to 4. Can you tell me the useful elements of your first window? 10 and 9, right? Because you initialize your deque with 10, and now you see that, hey, this thing is smaller than this, so it will come. When this 2 comes, you compare this with 1. So what will you do? This 2 will make this 1 useless. So this 2 will kick this thing out, but this 2 can't kick this 10 out. Okay. Now this 9 comes. So this 9 is greater than 2, so it will kick it out, but this 9 is not greater than this 10. So 10 and 9 are the useful elements of my first window. And so for my first window, the answer will be 10. Okay. Now move on to next window. So my next window is this. I welcome new element 7. What do? Whenever you welcome a new element, first you see whether some elements can be popped or not. Can you pop anything from here? If your next element is 7, can you pop anything here? You cannot pop, right? So you will simply insert this 7 over here. Okay. Somebody wrote in 10. So I said that with respect to insertion of 7, can you pop anything from this end? You cannot pop anything from this end, right? So you have to insert this 7 as it is. But now, since your window has slid, so you would check if the previous element, the front element belongs to the last window or not. Does this belong to the last window? Yes. So now you will kick this out. So now this much is your deque, and whatever is the front of it, that is the answer of your next window, which is from here to here. Let's keep moving on. Now this is your next window. 6 comes. Can this 6 kick this 7 out? No, because 6 is smaller than 7. So it will get inserted as it is. Okay, how about this? Should I kick this thing out? No. Why? Because this 9 is a member of my current window, because this index, if you check, will be greater than I minus k. So this has to be retained. So again, for the next window also, my answer will be 9. Now comes 5. Okay. So now this 5, when it comes over here, this 5 was smaller than 6, so it cannot kick anything out from here. How about this 9? Can I kick out this 9 now? This is my window, by the way. No, because still 9 is a part of my window. So again, my answer will continue to be 9. Okay, can you tell me what will be the maximum size of deque at any point of time? Yes, maximum size of my deque at any point of time will be order of k. And it will happen when that particular k-sized window is strictly sorted in descending order, right? Because when it is strictly sorted in descending order, all the elements will be useful. Now comes 11. So now this is the window that I am considering. When I am considering this window, 11 comes. How many elements can be kicked out by 11? So 11 is greater than 5. So any window that starts from 5 will contain it. 11 is greater than 6 also. 11 is greater than 7 also. And 11 is greater than 9 also. So I see that 11 is greater than all of them. So in that case, I can let 11 kick out all of these elements. So I'll have 11 located over here. And now the front of the queue is 11, which is not smaller than I minus k, so nothing is to be kicked out. So again my answer for this window is 11. Now again I move ahead. So now this 3 comes, so this 3 cannot kick out this, and this 11 is a part of the same window, so I can't kick out this, so again the answer is 11. So this is the way you can get your job done. Can someone tell me the time complexity of this approach? What is the maximum number of times I am touching an element? So at max, an element is getting touched 2 times, either while being pushed or while being popped. Okay, so it will be ordered 2 into n in the worst case. Imagine a scenario where all the elements are sorted in descending order. So every time you are pushing a new element and popping a different one. So it will never go beyond that. So it is an approximated to the order n algorithm. So I'm just going to write the pseudocode for it. I think rest you can do on your own. So how's the algorithm going to look like? So let's say I have my function is max window, and this function takes in the array, the size of the array and the size of the window. Okay, so I'll first initialize my deque. It is, I think, just QUE. It's a wrong spelling, but that is how it is in STL. Please check that. Okay, cool. Now the first thing that I'm supposed to do is I'm supposed to initialize my first window of size k. Everyone look at the board. I'm supposed to initialize the useful elements of my first window of size k by inserting them in the deque in descending order. Okay, so for I varying from 0 to k minus 1, what I'll do is you are trying to insert a new element, ith element in your deque. Before inserting it, you will pop out the useless elements from the rear end. So you will check it in this way, while not of q dot empty. You understand why I have this case over here? I have this case over here because I would try to compare array of I with the element at the rear end of the queue. And what if the queue is empty? If the queue is empty and if you try to fetch something from the rear end, you will get underflow exception. Also, this deque is not a deque of elements. This is a deque of indices. This is a deque of indices. Okay. So while the queue is not empty and my array of I is as long as my element is greater than equal to whatever is at the front end of the queue, sorry, whatever is at the rear end of the queue. Now the rear end doesn't contain element, it contains the index of the element. So I need to compare this with array of q dot back. I think this is q dot back or q dot rear. Please check on your own. Okay. So as long as this is the case, what would you do? As long as this is the case, you would want to pop from the rear end. You would want to pop from the rear end or back end, whatever you call it. So q dot pop underscore back. Okay. And when this is over, then you would want to do q dot push of I. So this thing has initialized the useful elements of my first window. Now what can I do? Now I can start iterating from I equals to k to n minus 1. Okay, so for that I'll have my I varying from k to n minus 1. Now tell me one thing. At the start of this loop, I will be having the useful elements of previous window. Yes or no? I will be having the useful elements of the previous window, and the answer for my previous window will be at the front of the queue. It will be at the front of the queue, right? So the first thing that I will do over here is I will print the front of queue. So just print the front of queue. So in ith iteration, you are printing the answer of previous iteration basically. Okay, and now you will check if the front element should be kicked out or not. Okay, so for that you will compare this q dot front is index. So if this thing is smaller than equals to I minus k, it clearly means that it should be kicked out. So you will call q pop front. So see, there was a pop back here, there is a pop front over here. And after this, now you would want to check if the new element, which is array of I, it can be inserted or not. So now you deleted something from the front end, and now you would welcome the new element at the rear end. But for that, you might also have to pop many things. So don't you think the same code, the same piece of code will come over here, right? Because your new element comes, you compare it with the rear elements and pop as far as possible, and then you push it. Okay, cool. So after this loop is over, you would have printed the answer for every window except one window. Can you tell me for which window the answer would not have got printed when this loop is over? For last window, yes or no? Yes. So the last thing that you need to do over here is print front of queue. How many of you can solve this question if I want you to find minimum in every window of size k? If I want you to find minimum in every window of size k, can you solve it? Okay. Can you tell me how will your deque look like? From front till rear, will it be sorted in increasing or will it be sorted in decreasing? It will be sorted in increasing order, right? Because now if a greater element comes after you, then that cannot stop you from staying the answer for your window. But if a smaller element than you comes, let's say there was a 10 here and there was a 1 here, and let's say the windows are of size 4. So any window of size 4 that starts from here will contain this 1 in it. And this one is smaller than this, so it will not allow this to be the answer. So this is the way in which you can get your job done. Okay. And let's say, so basically this one would kick this thing out, and let's say then 11 comes. Can 11 stop this one from being the minimum answer in its window? This cannot, right? And let's say after this something like 6 comes. Can you tell me which all element will be popped due to this 6? Just 11 will be popped, because any window of size 4 starting from 11 will contain 6 in it, and 6 being smaller than 11 will not allow 11 to be the answer. So the useful elements of this window are 1 and 6, and whatever is the first element, that is the answer. So the same approach is going to run and we'll get the job done. Okay, great.